if I have a vector A heading in this direction, what does the negative vector of that look like? What's the difference? Describe it to me in words. It goes the other way. Opposite direction. What about my magnitude? Same magnitude. So I'm going to try and draw it really nicely. This vector would be known as minus A. Yes? Confirmation, we're all good with that? So when we deal with subtraction of vectors, it's actually the opposite. We're just going to add the opposite direction. So if I had A, we're going to use the same values as here, minus B, it's the same as if I had A plus the vector B in the opposite direction. Who would like to tell me what that changes? Let's go in column format. What would it look like now? In column format, same example. Don't give me the answer. Tell me what it would look like. What's my A? 1 and 2. What's my B? Now it's 3 and minus 5. I could either put my plus here or I could put a 3 and minus 5. I'll show you what that looks like as a plus. Are we happy with that? My answer ends up being minus 2, 7. Have a look how that compares to my original answer. What's the difference? I had minus 2, 7. Have I done a mistake?
Yes.
I have. Of course I have.
Yeah.
Did I write this one wrong?
Yeah.
Yes.
Yeah.
Yes. No, other way around. Plus 3 minus 5. Got it?
Yeah.
I'm like, no, it's not meant to be the same. What do we get? 4
4 and minus 3.
and minus 3. So have a look. It is different. Let's have a look graphically why we would expect it to be different. Here's my A vector. Here's my B vector. When I added them before, I ended up with this vector. I'm just going to write that off here. Agreed. When I did my minus B, I turned this around so its head was down here. But now I have a head to a head, and I can't add that way. What I have to do is slide it down to be on the tail. So I take my B and I turn it in the other direction and I slide it down to be head to tail. Are we okay? Let me put some letters around that to see. If this was O and this was A and this was my point B, I'm going to change this one to be B. Where is my resultant answer now? Which letters is it going from and to? It's going from B to A. Let's have a look at what we've drawn here. What does this shape look like? A parallelogram. Notice one of the diagonals of my parallelogram is A plus B, and the other diagonal of my parallelogram is A minus B. A plus B, A minus B. Are the diagonals of a parallelogram equal? No? Are there certain parallelograms for which they are equal? Which parallelogram has equal diagonals? Squares? Rectangles? Rhombus?
No, it's not equal. They're perpendicular.
It's not equal, they're perpendicular, and that's important for later. But our squares and our rhombuses have, sorry, our squares and our rectangles have equal diagonals. Agreed? But we are a parallelogram. It's called the parallelogram law. It also tells us a lot about our addition. So again, if we were to have A plus B vector, we could go around the other way and say, ooh, sorry, B plus A. What does it mean if we have that A plus B equals B plus A? What's the word for this? Commutative. Good. All right. Addition in vectors is commutative. Subtraction, not so much. If I turned this around to be minus A, we would end up with an entirely different thing. So we don't have commutative, which is sort of what we expect. Do you agree? Okay. How are we going so far? We can do addition in component and column form. We can do a scalar multiple. We can do subtraction in component and column form. I just want to now, and I'll erase this a little bit, have a couple of interesting discussions about special vectors. What can you tell me about these two vectors? They're equal. Do you agree? Are they necessarily sitting on top of each other? Why not?
Different origin.
We don't know what their origin points are. Agreed? If we added them, we've basically doubled where we're going. But what happens if we subtract them? What do I end up with if I subtract them? Again, I hadn't shown you one in component form. What do we end up with? 0. Is it 0 or is it a vector? The answer, we have a vector because we have a vector addition, or subtraction in this case. We had a vector, we subtracted a vector, our resultant is a vector. But this is a very special vector. It's a vector called the 0 vector. We're very creative. It's got some special features. What's its magnitude? What's its direction?
No direction.
It's got no direction. However, a special feature of the 0 vector is that we say these two vectors are parallel. Do you agree? The 0 vector is parallel to itself and all other vectors. It pulls out the trump card and it says, you know what? I don't have a direction, so I'm going to be parallel to myself and everyone else. It's one of those things that, I don't know, if you're like me, you look at and you go, why did we bother defining that? But it needs to be defined. What happens when we end up as a point? Okay? What happens as we end up as a point? Those of you heading into, eventually, three-dimensional vectors in extension 2, the concepts that we have of being parallel and the concepts we have of being a 0 point with no direction start to look a little bit more skewy, and we need to define them and really closely nail them down. And this is one of those first things. Now, I very casually asked you guys, are these two vectors parallel? And you went, yes. Another one of those fine points that we need to think about is they are only parallel because they can be represented by two line segments and the line segments are parallel. Doesn't make much difference at this point, but this is why we can define them to be parallel. Alright, the last thing before I set you guys working is, what happens if we add more than one vector? We no longer can play with our triangles or our parallelograms, but let's just draw a nice generalized diagram of, let's say, 3 vectors. A, B, and C. Let's call this O, A, B, C. Can you tell me one vector that would be the resultant of vector A plus vector B plus vector C? It would be OC. This is you going down to Cherrybrook Shops, then up to Boundary Road to get the bus, and then finally getting home. You still could go directly home from school and you would still get there. Alrighty? So this is vector OC. Now this one might look a little bit silly, but let's say you decided not to go to Cherrybrook Shops, but instead you decided to go straight up to Boundary Road and then head home. Have you ended up in the same spot? What's this vector? OB, can you give it to me in terms of A's and B's? A plus B. So, and this again might be one of those things that you look at and go, duh. A plus B, doing this first and then adding C. What happens if I decide instead to go straight from A, I'm running out of colours, straight from A then to C? What's this vector? B plus C. Oops, sorry, no black there at all. B plus C. So this still gets me OC, do you agree? So I have A plus B plus C. And all of them are the same as A plus B plus C going straight. Do you agree? What happens when it doesn't matter the order that I do them in? Not commutative. What's the other one? Not commutative. I like it, but no. Starts with an A. Associative. So vector addition is commutative. We can do it either way round. And associative, we can stretch it out and do it in different components to get there at the same time. This will become important when we're doing our practical applications at the end of the topic, because sometimes it's easier to add a different set of vectors first. And you can do that. You can't subtract, but you can add those different vectors.